learn a little bit about mathematics. Today, we're finishing off 16.4, at least that's my goal. We're going to do Green's theorem, which is essentially a way of finding a closed loop line integral. One of the versions of it looks like this. It says, like, the integral on C doing a positive orientation, which is anti-clockwise, can be rewritten as a double integral of the region D. So if you imagine this is the closed loop for C, D is the region inside it. So C is a closed loop, it's positive, D is a region bounded by C, and dA, because it's now going to be turned into a double integral, has one of two choices. You're either going to do the dx dy or dy dx, depending on what makes more sense to you. And sometimes you'll do polar. You will do polar if the curve CR, the region D, whichever way you want to look at it, is circular in some way. So here's an example of that question. We'd like to do this closed loop. Oh, do you see that funny little circle around the integral? Okay, say hello again there. And that notation means that it's a closed loop. And if you don't have it, it doesn't mean that it's not a closed loop. It might or might not be. So in the entire section 16.4, since every single one of them is a closed loop, they could have went back there and said that, right? So just a little inconsistency in notation. So you're going to see some questions where you see that little circle, and then you're going to see some questions where they're not. In the context of this section, everybody is a closed loop. So you're doing the same thing regardless. Now, since I want to do this line integral and it's a circle, I'm pretty sure polar is the way to go. This fella is P. This guy is Q. Since it's a circle of radius 5, won't that essentially give me, and since it's a complete circle, it gives me that, right? So we're pretty much ready to go. It's going to be a double integral. I'm going to differentiate this with respect to x, which is 1. Take away, differentiate this with respect to y, which is -1. Whoa. I'm going to do polar. And that means r is going to go 0 to 5. And theta is going to go 0 to 2 pi. And then I'll tidy it up a little bit. I'm hesitant here because it's too easy. Is there anything I've done wrong there, or is it just a very easy question? I think it's just a very easy question. I'm looking at it, I can't see anything obviously wrong with it. Okay, variable separable. So I'll do that guy. And that fella, this guy's going to be 2 pi. This guy's going to be r squared. So it's going to get me 25 times 2. And the line integral is 50 pi. Are we okay with this question? It just feels a bit simple, but I guess I'm just untrustworthy. I keep thinking there should be something a little bit uglier, and maybe sometimes like this there isn't.
Sometimes it works out.
Yeah.
Sometimes it just works out.
Yeah, sometimes it just works out. Okay. Let's focus on circles for a little while, and then we'll look at other situations. Triangles are a good choice as well. Let's see if I got any. I got a circle, done that one. Triangle, rectangle, don't want that. Triangle, don't want that yet. loop the loop, don't want that. That's interesting. And this one is interesting. Okay. This is question 12. The information is given by telling us what the vector function is, right? The vector field, it's, you know me and scanning, so trying to focus. Right, that's the guy. And C is the circle. X squared plus Y squared equals 1. Okay. Since the closed loop is a circle, would you agree that's polar again? I mean, there's no argument to me. If you see circle, I think it's just going to be that. So that's going to give me, in this case, 0, 1, and it's a complete circle, so 0, 2 pi. Now, because the question is just phrased as find the line integral, that's P and that's Q. Does that make sense that the first guy's called P and the second guy's called Q? So we want to get the line integral. Just write it in that generic form. It's going to be the double integral over the region D of this fella, dA. Okay, let's see. If you differentiate this guy here, right, this guy here, with respect to x, you get negative y squared. Take away, if you differentiate this guy here with respect to y, you get that guy. And since it's going to be polar, it's that fella. And that means I can do r equals 0 to 1 and theta equals 0 to 2 pi. Okay. What will negative x squared, negative y squared be when you convert it to polar form?
Negative r squared?
Yeah, negative r squared. So this is going to be 0 to 2 pi, 0 to 1, negative r squared times another r. Oh, variable separable, which I like. So 0 to 2 pi of 1 and 0 to 1 of negative r cubed. I could do this in my head, 2 pi. I should be able to do this in my head. It's a quarter with a negative. So it's negative a quarter. And so the answer looks like, and I phrased it very carefully, as the answer looks like it's negative a half pi. But it's not. If you look at my information that I got from question 12, is there anything in there that may make you change your answer away from negative a half pi?
Oriented clockwise.
Correct. And how do we fix that?
Switch a sign.
So, although you can do exactly the work, will you just remember to do that after the event? And you can put a little arrow, something like orientation, you know, just so people know what the reason you just didn't do it because you felt like it. Do you see how like a little word like that could easily just disappear in the process? And you keep looking at it and you think, it's right. Well, it was 99% of it was right. Just a little bit at the end that threw us. Now, this is a side note, so it's not a specific question, but I want to show you how you can do a little fiddle. I want you to imagine that my closed loop generated, say, half a circle. Right? Okay, we could do that. And we could get the line integral of whatever it is, and let's pretend that the answer is 42. No biggie, right? You've done it. But suppose the question was really just that part, from here to here, nothing else. How could we find it using Green's theorem? Well, we know this answer, right? So call it FDR. Can't you just subtract that little line integral? But isn't this line integral just a horizontal line, and you could do it the good old-fashioned way, 2 sections back? And that might well be less work than trying to do this from scratch. Because if you did this from 2 sections back, can you trust me that in a lot of circumstances, the integrals that you get are horrendously big and ugly? Whereas Green's theorem might be very easy, it's 42 pi. And then you have to do a little baby line integral, which you would subtract. And what would be left would be that guy. So that is not a question that you've been asked to do. I felt it would be worthwhile just to show you that there are strategies where you can use Green's theorem to find a line integral that's not a closed loop. You pretend it's a closed loop, and then you just subtract the bit that you use to join it up. And that might be a better strategy than calculation-wise. Now, this one here is the last circle one that I want to do. And it's a closed loop that looks something like this. And C is phrased in a way that doesn't make sense to me, but I do know what they mean. Is bounded, is the boundary, that makes better word, is the boundary of x squared plus y squared plus x equal to 9. And x squared plus y squared is 49. So what we basically have here, do you notice that this is basically a donut? And so the region D is much easier to describe than C, but it's the region bounded by this fella. And what does that look like? It looks like this. So it's really just a big circle inside the little, or a little circle inside the big circle. So if you take all of that gunk, it basically just says that you've got a circle between 3 and 9. And you do. Question?
Yeah. The red arrows are pointing opposite ways from each other. Was that just okay?
The reason why, that's kind of what they have to do, because on this one, isn't the area to the left of you as you work around? See the outside loop? As I walk around it, the area has to be to the left of me. In the inside circle, as I walk around, doesn't the area have to be to the left of me? So that's why the one goes clock and the other goes anti-clockwise. If you want to see the theory of what the heck that is, you arbitrarily put a little split in that and you go and you join them and the two little lines cancel each other out. It's messy, but the good news is it's easy to do because that's D. And that's really what you need to know. Now, in this question up here, this fellow's going to be P, and this guy's going to be Q, as always, right? So since I've taken up so much room with that, this guy, which I won't write again because he's here, is a double integral. And that's what R goes from 3 to 7. And theta goes from 0 to 2 pi. And then it should be d by dx of q, take away d by dy, p. And since I'm doing a polar, I'll write that down like that. So I need to take, what do I need to take? I need to take this guy with respect to x. So let's see what we get. This guy with respect to x. Oh, I don't like that. 4x cubed plus 4xy squared. Take away, oh, I like that. Take away 0. So at least we get something out of it. So it's going to be 0 to 2 pi, 3e7, 4x cubed plus 4y squared, r dr d theta. Now it's pretty obvious that we're not going to leave the x's and the y's. There should be an x in there, right? So let's think of style points before we do anything. Is there anything you can do to 4x cubed plus 4xy squared that might help later on? Four x cubed plus 4xy squared. Anything algebraically you can do to that?
Take an x out.
Okay, I might as well take a 4 as well while we're at it. And that leaves me with that. Do you now see that that's going to be a little bit prettier when we go polar on it? Because won't x squared plus y squared be r squared? 4x, not so good. Isn't x r cosine theta? So that's going to be 4r cosine theta. And we're going to do what, a 3 to 7 and 0 to 2 pi still. It's variable separable. I'll take out a cosine. And I'll do a 3 to 7. And what do I get? A 4, an r squared, another one. I basically get 4r to the 4 dr. And at this point, I'm dotting it. Now, if you didn't pull out the 4x and you left it this way, couldn't you just turn all the x's into r cos thetas and turn all the y's into r sin thetas and then pull out some common factors, and it would eventually end up being the same thing? It just seemed to me a little bit easier to do it with x's than it would have been to convert it immediately into r coses and r sines. Are we okay with that particular one? Things going good so far? Green's theorem is essentially double integrals. Watch out for positive orientation or any orientation. So let's change tack and do triangles. Let's find a triangle. How hard is it to find a triangle? That's a rectangle. Don't want a rectangle. It must be a triangle. I saw one a minute ago. Oh, here's one. If I was really good, which I'm not, I would be picking my own questions. But from experience, if you randomly pick a function and randomly pick a closed curve, isn't there a very good chance you end up with some ridiculously ugly answer because nothing comes out nice? So I've kind of learned my lesson lately to not do that. Now this fella, C, is a triangle that's joining these 3 points together. So in this particular situation, I would start by figuring out where the guy goes. So let's see. Here is our triangle. And if you join them up in the order that they're written, it's positive orientation. So we are going to do the dx dy version. Actually, it'll be the dy dx version. This is P, this is Q. This is D. Now, I'm going to describe D in terms of the range of values of X and the range of values of Y. The orientation of this triangle makes me see this. I'm going to do X goes from 0 to 2. Y, on the other hand, is going to go from triangle at the top to triangle at the bottom. So this line here, right, and this line here are going to be converted into equations of lines of the form y equals, and whatever this one is, it's going to go on the big side, and whatever this one is, it's in the little side. You agree, a little vertical line, top line, bottom line. Okay, this one goes through the origin and it passes through the point 2, 4. Would it be okay for me just to say it's pretty obvious that it's y equals 2x? Would you agree that the origin to that point 2, 4 is the line y equals 2x? What would be the second one, this lower line? What would its equation be?
Just y equals x.
Okay. So over here, right, are you now happy about how I described the region D in terms of x and y, which is kind of what you have to do with triangles, right? Polar's not going to help with a triangle, it's never has. Right. Well, we got it all set up. The original integral, which I'm just going to call that, it's going to be the double integral over D, this fella, and we know it's going to be a dy dx. How do I know it's a dy dx and not a dx dy?
The bounds of y's have x in it, is in function of x.
Agreed. Okay. A little thing, but you want to get it the right way around, right? So let's find out what the pieces are. So that's going to be x goes from 0 to 2, and y is going to go from x to 2x. That's not too bad. Differentiate this guy. You can't see it, but I'm pointing at him. I should bring it down a little bit there. Differentiate this guy with respect to x, and you get 10xy. Take away, differentiate this guy with respect to y, and you get 2xy. And then you're going to have a dy and a dx. And so the answer is x equals 0 to x equals 2, y equals x to y equals 2x, axy, dy, dx. Okay, is this variable separable?
Yeah.
Well, I heard both answers. Which one is the right one?
We can't really because of the y.
Right? So you have to do the first and the second. Would you agree that that's something you've seen harder versions of, right? You should be able to finish that off now. So I won't take it any further. So you're going to integrate with respect to y, plug these guys in, then integrate with respect to x, and get your 42. Are we comfortable with triangles then? Right, we've done circles, done 2 circles. We've done rectangles yesterday. And we've done triangles today. Pretty much everything. Oh, and we did a cosine yesterday as well, didn't we? Now, let's see if I can find another triangle. Okay, can't find another triangle. So let's do a curve. Our last question for today. Well, there's, yeah, it is the last question. I'm not changing that, but there's something else I have to tell you. Okay, that's the guy. Now, C is described, God, it's, let me just read it. I don't want to write it. C consists of a line segment from 0, 9 to 0, 0. And then it goes from 0, 0 to 3, 0. And it does a parabola. Well, I guess I'm writing it. It does a parabola. Y equals 9 take away x squared from 3, 0 to 0, 9. That is a lot happening. So let's get the P and the Q done. Okay, I really need to draw this. I can't do it without that. Okay, so orientation is important as well. So 0, 9 can be here. And I go to 0, 0, which is here. I put a red line on my journey. So that's a straight line. And that's the beginning of my curve, right? So it goes that way. And then 0, 0 goes to 3, 0. So say it's there. And it goes this way. The parabola 9 minus x squared looks like this. And it's to go from 3, 0 to 0, 9. You know, I think they made a meal of that. That could have been described a lot easier, couldn't it? So there's your region. Positive or negative orientation?
Positive.
Agreed. Right, as you walk around, that shape is in the area to the left. That's positive. Anti-clockwise, if you prefer. So we've got all the pieces. Great. I need to set up, I don't know why I moved that yet. I need to set up D. I would say that this is orientated with x's going from 0 to 3. How would you orientate the range of y's? What would they be?
Will that be from 0 to 9 minus x squared?
Yes. You agree? Y goes from the bottom, 0. Can you imagine one of my little, it's been a while since I've done these guys. Remember my little rectangle? Gives me bottom to top. Y is 0 at the bottom. Y is the curve value at the top. So 0 to 9 minus x squared. So that's this fella. Okay, now we've got all the pieces. That integral is now going to be a double integral over the region D. This guy with x, take away this guy with y. We're going to do a dy dx again. The range of values of x are going to be from 0 to 3. And the range of values of y are going to be 0 to 9 take away x. If you differentiate this, oh. Does anybody know why I'm doing a double O?
It's just gonna 0. That's just gonna be 1.
Right, if you differentiate this with respect to x, don't you get 0? And if you differentiate this with respect to y, don't you get 0?
Oh, shoot.
Do you know what that just told me? If I had bothered to figure that out, I shouldn't have even needed to have worried about what the darn shape was.
Because it's a conservative field?
Because it's a conservative field, exactly. Most of these guys are not conservative fields, right? Most of them are not, and that's why you need to do Green's theorem. Because if they were conservative fields, isn't there a property that says every closed loop, which basically means if you start and finish at the same point, doesn't a conservative field give you 0 for the line integral? Right? You remember the value of the function at the beginning, take away the value of the function at the end, it's the same function, so you get 0. That was a sneaky one to finish, but nice, because, you know, I like surprises. I guess the moral of that story should be, find this before you start working on anything else. Because if this ends up being 0, won't this be irrelevant? Okay. So a couple of things. We're finished with questions, as I said. Obviously, there's some things I want to talk about. Mostly what the test is going to be like. But before that, there's something I want to show you in the homework that may throw you. But you'll like my answer, so it won't. Right, double check. Are you looking at Green's theorem homework? Are you saying what you should be saying here? Right. Maybe make it a little bit bigger, because I don't know what kind of screens some of you have got. Yeah, maybe a bit easier to read. Standard questions. Nothing going on here that I need to mention. If I keep going, eventually I'll get to it. There we go. Question 7, for instance, asks you to do it directly, and then it asks you to do the same question using Green's theorem. Now, when they say directly, what they're really meaning here is, do you remember the parametric form where you find R of t and you replace all the x's with whatever they are in t's and all the y's in terms of t, and don't you replace the dx by whatever it is dt? You know, that whole process is quite big and cumbersome. That's what they mean by directly. And Green's theorem is what we've been doing. You know, both answers are the same. I mean, because it's the same question. So the answer to this is dead easy. Don't do it directly. But to keep WebAssign happy, do that answer. And if it's 42, will you make that answer 42 to keep it happy, right? Because you can't just leave it blank, or WebAssign will say you're wrong. Okay. So if it asks you to do it using Green's theorem and directly, will we just reduce that question to do Green's theorem, right? You've had plenty of practice at doing it the other way. I'm pretty sure I know why they did this. They're kind of wanting you to say, look, Green's theorem might look like magic to you, but really it works. Here, look, see, we've done it both ways. See, it works. All right, a kind of convincing by example, right? If you do enough examples and both ways work, you're more likely to be convinced that Green's theorem is true. But you lot are very trusting, aren't you? So do you believe Green theorem works? Right. I believe it totally. So don't bother with that. There's another one where you don't do it. There's a triangle. There's another one where you don't do it. There's a circle one, we've covered that. And that's that one. So we are finished as far as that's concerned. So a few minutes left. Let's talk about your test. Yes.
I do have a question. When you are graphing vector fields, where do you go for that?
Oh, what program?
Yeah.
Okay, let me see if I can find it. Here, oh, I'll put it over here and that way you can see what I'm saying. Go to dashboard and go into our classes. I should have it there. I don't know why I don't. If I didn't, I apologize. Advanced, basic, right, here we go. Vector fields 2D.
I might have totally forgotten that was there. Okay, never mind.
Vector field 3D. Desmos is kind of cool. You know that your line integrals are 2D. And so if you wanted to see what, some of the curves would look like, I guess you could do Desmos, if you wanted to. Oh, I've got that version. That's not very nice, but never mind, it works. Are we cool with that question then? Any other questions before I talk about the testing? Cool. Okay. So obviously, here we go. That should be bigger. Can I make it bigger? We're getting close to the end. It's surprising how quickly a quarter goes when you're enjoying yourself. Okay, homework is due, of course, on midnight. Your test is 16.1 to 16.4. That's pretty straightforward. You got 2 hours, so, you can get long questions. My gut feeling is right now I'm probably going to do 2 questions from each section, so there'll be 8 questions in the test. I haven't made them yet. I like to do them over the weekend when I've got, time and no other distractions going on. I'll see you at 8. Isn't everything pretty much? I'm a boring now. You know how I do things. Your turn up and WebAssign will appear. You can't, talk to people about the test. All that stuff is exactly the same. And once we've finished, just 4 more guys to go. Some really cool stuff. Then homework is due, and you've got test 5. Now, what I haven't told you, or at least I don't think I've told you, is that you get 5 tests, right? Obviously, test 5 is on the last one, and it's on Monday, and then your final exam is on the Tuesday. But I only count the best 4 tests. So if you've got really very, very good 4th tests, you don't need to turn up on Monday, because I'll give you the attendance anyway for Monday. And you can use that time just to get ready for your final and focus on doing that. If you've got a bad one or you think you could improve on it, then you should really turn up for test 5. If test 5 ends up being really horrible, it won't affect your grade because I keep the best 4, right? So you're still going to get the grade you would have got. So I guess that might reduce the stress a little bit. Best 4 out of the 5 counts. And then your final is on everything. Are we good? Is there any questions? Because we kind of finished at a nice place here and I don't want to do any more. We should finish on a joke then. Right, say hi while I think of a joke. I may have told you this one. I've told so many, I don't know. Yeah, it just came into my head again. Why don't oysters buy you presents?
Why?
They're shellfish. Why are mountains so funny?
Why are they?
Because they're hill areas.
Hilarious. I get it.
Okay, just shake your head and walk away, Chris. I can handle it. Okay, guys, I'll hang about for any homework, anything you might want to ask. Otherwise, have a nice weekend, but not too nice a weekend because you've got tests coming, right? And I shall see you on Monday for your test.
Bye.
Bye, guys.
There it is. That's funny.
You like that one? How do you know? Anna, did you like the hilarious question?
It was okay.
It was okay, good.
It was hilarious.
Oh, Chris did a pun on my joke. Oh, shame on you, Chris, to resort to that level of humour. Shame on you.
I think it was influenced.
Oh, God, do you think I'm having a bad influence on you now? Yeah.
I do have a question.
Okay, let's get started. What's your
Would I
question?
be able to take the test from 9 to 11 because I do have chemistry on Mondays?
Not a problem. All you do is shoot me an email and tell me your time slot, and I will. When you go into WebAssign, there'll be something called Christopher's test or something, and you know that's the one you'll take. Right?
Okay.
The only difference is you won't have the time to upload your working, so you'll have to upload it and send it to my email address instead of using the Canvas upload feature. Right, that's
Still
all the
convert it to a
difference.
PDF or?
Yep, and put it as an attachment to the email. Just say, here's my working, attach the email, and we're good to go.
Okay, awesome. Thank you. Have a good weekend.
You too. Okay, who's next on the list?
I just had the same question after like what we've always been talking about switching.
Yeah.
Okay, I was gonna send you an email to remind you.
Just do we're getting into a routine now, aren't we?
Yep.
That's
Okay,
how we
right.
do it. Not a problem.
Thank you so much. Have a great day.
Oh, wait a minute before you go, Brooke.
Yeah.
You still here?
Yeah.
Is your time slot the same as his or yours the earlier one? I can't remember.
As the other one, the 7 to 9.
Okay, so I can't kind of share the same test. I have to do one for you as well. No problem.
Yeah. All right. Have
No
a great
problem.
day.
You too. Bye-bye.
All right. Bye-bye.
Okay. Who's next?
I have the same issue.
Okay, what time slot are you in now?
The same as Chris's.
Right, so you just
So
shoot an
it's,
email. Right, because of chemistry, right. Well, can you shoot an email, just tell me specifically the time.
Yep.
So when that test appears, it probably won't be called his name anymore. It'll just be called the 8 to 10 test or the 7 to 9 test, whatever the time slot
right.
is. Okay.
Thank you.
You're welcome. Okay, who's next?
I had a question about, so actually I had two questions.
Go for it.
I see that that on our Canvas page you have like those lecture videos from like
Yes.
from stuff. So I was wondering if you could upload the one for chapter 14, so I can see. Right now I'm only seeing 15 and 16.
Let me check what's going on here. You want 14 up?
Yeah, please.
I
if you don't
got you.
mind.
Not a
Just-
problem. It shouldn't take more than a few seconds for me to do that. So if you could just hold off, I will
Okay.
find it and drop it in.
Okay.
It should be down here under whatever I called it. It's not that. Useful resources. Doubt it's called that.
Yeah, they're pretty good.
There it is.
So-
Chapter 4, lecture notes, all that good stuff. Bring it
Yeah.
up.
They're pretty good. I mean, they've been kind of helping me out a little bit. Like if I don't understand something, I just get online, kind of just look up.
There we go.
look up some videos.
It's there now. Should be able to see it.
Let me see. Yep, it's up. Thank you.
Right. What else?
And my second question was, so what is the gradient of F? I completely. I mean, it's been a while, so I'm.
What is the gradient of F? What does it represent?
Yeah,
Okay,
what does it represent exactly?
So, kind of visual thing. I want you to imagine that you've got a function, right? X squared plus y squared, right?
Okay.
Now, if you plot all the points, this is a contour plot, it's called. And what you do is you basically plot all the points where f of xy is equal to, say, a number like 1. Well, if you do that, you get this fella, and 1. And if you do a 2, and if you do a 3, and you do a 4. So I'm picking a circle because they're quick and easy to draw. So
Okay.
this is called a contour plot of this function. It's a way of trying to visualize what it would be. It's a bit like you know, a map that you might have got if you were in the military, and a contour map. You could actually look at this and say, oh, there's a hill there, and this is the shape of it. And each one of these represents all the points with a height of 1 and all the points with a height of 3. Right?
Okay.
So far, so good.
Okay.
Now, if you take a random point, let's say a point here, right?
Okay.
And you find the gradient of the vector, which we know is what, 2x comma 2y, right?
Right.
And if you find the value of that at this point here, right, What you get is a vector, and the vector points this way. It's at right angles to the contour line. So what the gradient is doing is saying, look, on this point on your surface. So if you can imagine this was a surface, it would look probably something like this. And this would be the z-axis going all the way up, right?
Right.
If you take a point, the vector that you get, the delta vector, is a point that's pointing away from the surface at right angles to what you might think at that point. So you can imagine there's a little plane, a little piece of paper, and you are like this. You're pointing right out of it. So that's what it is.
Okay.
So in a geometric sense, why can that be helpful? Well, if you choose a point and you look at the gradient vector, it tends to be the steepest direction that you would climb up or down that surface. So if you're on a surface, imagine this is, that's a very weird surface, but imagine it was a hill, right?
Right.
If you're on that hill, what direction would you be looking at if you were looking at trying to go like in the steepest direction? That would very often be it. It would be uphill or downhill. And so it can be used to do that. And that's why the gradient vector is used in the Lagrange things. Remember those guys where we used it to find max and min?
Okay.
That's where they come in.
Okay. Okay. I see it now. And then the directional vector is the value of it, pretty much.
The directional vector is the derivative of the curve at that given point looking in this particular direction. That's not an easy one to say. It's a very 3D thing. Can you imagine that you've got a surface, right? That's more realistic, right? You got a surface and you have a direction V, and you want to get the direction vector at a given point. Well, what you do is you cut that shape with a knife, using that vector as your knife. And when you do that, you will make a single curve in 2D space, and the slope of the line at that point on that single curve, that number, is your directional derivative.
Oh. Okay.
So if you do a directional derivative 1, 0, basically you're slicing it in the 1 in the x direction, right? You're slicing it like this way.
Right.
And if you do a 0, 1, you're slicing it that way. So aren't those two just special examples? They're called df by dx and df by dy.
Right.
All a directional derivative says is, well, you don't need to cut it parallel to the x or y axis. What happens if you do it like a direction 1, 3?
1, 3, exactly.
And if you cut it in that direction, at any given point, there's a curve now. Can you imagine if you take a surface and you cut it, all you have is a 2D curve now. And that 2D curve has a slope at any given point, and your directional derivative is the value of that slope at any given point.
Okay. Okay. All right. That makes a lot more sense now. Okay.
It's probably one of those things you should go looking for a good animated video.
Yeah.
Right. Somebody does some animation, they take a surface and then they take the vector and they slice it like a cake, and then they zoom on the cake, and then they show you the little, the
little different
tangent line and what the
and
slope of that tangent line is, and the graphics might, because it's a very visual thing. I can imagine in my brain, because that's just the way my brain works, but it is what it is.
Yeah. No. I understand now.